All right, good morning, everyone. Let's go ahead and get started. Today, I am very excited to introduce Dr. Robin Canup. Robin is presently the Assistant Vice President of the Space Science and Engineering Division at Southwest Research Institute in beautiful Boulder, Colorado. Robin's career has been decorated by many awards and honors, including election into the National Academy of Sciences in 2012, the American Academy of Arts and Sciences in 2017, and recently was selected to co-chair the 2023 to 2032 Planetary Science and Astrobiology Decadal Survey. So Robin's research applies both analytical and numerical models to study the formation of planets and their moons. And today, we are so excited to hear about the origin of Earth's moon. Please join me in welcoming Dr.
It is such an honor to be here to address you all. Thank you for the kind invitation. So the origin of the moon is a project that I have worked on and off for many years. We think the origin of the moon is linked to the final stages of Earth's accretion. So as we understand how the moon formed, that in turn constrains the condition of Earth's accretion and the initial conditions of our planet. And in addition, by virtue of its proximity, we have a lot of data about the moon, an unusually rich data set to challenge our theoretical models that I think make it a very interesting problem as well. I'm going to start by talking about the canonical giant impact, the challenge to this idea that is brought by data that shows that the Earth and Moon are essentially identical in their isotopic compositions in many elements. Talk about several leading, I think, contenders for resolving this conundrum, and then areas of particular interest looking forward. So here are the most basic constraints of the Earth-Moon system. For a moon, the moon's pretty massive, contains about 1% of the Earth's mass. We know from its bulk density it's severely depleted in elemental iron. There's been a very large degree of modification of the lunar orbit over the 4.5 billion year history of the system. Tidal interaction between the Earth and Moon slows the Earth's rotation, causes the Moon's orbit to expand. This interaction conserves angular momentum. So the current angular momentum of the Earth-Moon system implies that when the Moon formed close to the Earth would have been rotating at about a 4 or 5 hour day. The giant impact theory was proposed after the Apollo missions. The first three-dimensional hydrodynamic simulations of these giant impacts were performed by Willie Benz, Al Cameron, and colleagues. And these showed that you can actually have, during one of these collisions, substantial material that ends up in a disk around the target that does not either re-impact or escape. And the reason you get the material in a disk is largely by virtue of gravitational torques between the material in the impacting object and the distorted shape of proto-Earth right after the impact, or torques across the material of the impactor itself, which is disrupted by the collision. In the early 2000s, we were able to identify the specific part of impact parameter space associated with the masses and angular momentum and iron depletion of the Moon. That was much later termed the canonical giant impact. And it's now understood that you don't have to finely tune the impact conditions to produce a disk. Actually, many, if not most, big impacts at low velocities will also produce a disk around the target. I'm going to show a couple simulations of a canonical impact that utilize the Lagrangian hydrodynamic method, smooth particle hydrodynamics, SPH. So we're describing the colliding objects with proto-Earth. The impactor that led to the formation of the Moon is often given the name of Theia, and I'll refer to it as such. So you describe Theia, the proto-Earth, by a multitude of particles. Each particle is representing a fixed mass and composition of material. The size of the particles adaptively adjust to the local density. Particularly important in moon-forming impact simulations is an equation of state that accounts for phase changes. The most important is vaporization, because the latent heat of vaporization for rocks is such a big energy sink in these simulations. And while SPH is probably the most commonly used method, many Eulerian grid codes now are also applied to this problem. So this is going to be a simulation of one of the original simulations from the 2004 paper of the impact of a roughly Mars-sized object at a low velocity and about a 45-degree angle. You'll see the distortion on the shape of the Earth that I mentioned earlier. The impactor will be ripped apart by the initial collision. A large clump of impactor material recollides with the Earth early on in the collision, and then there's a later close pass of a large clump that gets tidally stripped apart to form the ultimate disk. Yes, so both objects are assumed to be of chondritic bulk abundance, to have differentiated into silicate mantles and iron cores, where the latter comprise about 30% of their total mass. And so one of the goals of these simulations is to establish that you can form an iron depleted moon, even if the two objects that collided had generic solar system abundances. So yes, that's built into the simulation. So there you see the distortion on the figure of the Earth. This is the early on impact, secondary impact I mentioned. In the canonical impact, that object is mostly the metallic core from Theia. So with that secondary impact, it's primarily a geometric effect because the core is more central. The core of Theia tends to be mostly absorbed by the Earth, forming an iron depleted disk. Now the viewing angle is shifting. You see the passage of an outer clump from the impactor within the Roche limit of the Earth. It gets tidally stripped apart. After about a day of simulated time, you're left with a rapidly rotating Earth, about a 5-hour day. It has a silicate vapor atmosphere, red particles at low pressure, and it's surrounded by a disk with typically between 1.5 and 2 lunar masses. So many of these impacts that are around either head-on to quite grazing produce iron poor disk. That's a relatively simple part of the problem to address. The topic that will occupy the rest of my talk relates to the source of the material that ends up in the disk. With a Lagrangian code, it's very trivial to take your final disk, which we're looking at here in just a 2D simulation, and map back the place where the material that ended up in the disk originated from. And when we do that for canonical impacts, we find that the material that ends up in the disk overwhelmingly originates from a single region on that impacting planet, on Theia. It's this region that just grazes past the target. So the impact is going in this direction in this frame, okay? And so it's this region here of the impactor that's most effectively torqued into orbit around the Earth, and that'll prove to be very important. There have been many, probably thousands of impact simulations done at this point by many groups, not just myself. These are results of, again, a single canonical impact simulation done at various resolution in SPH, and then also with a 3-dimensional grid code known as CTH. And across these different simulations for this class of impacts, there are commonalities. First, the disk, as I said, always originates predominantly from Theia. Second, the disk is a mixture of melt and vapor, but after these class of impacts, it's predominantly melt, 80–90%. You can see in these different simulations something that's a common outcome, which is large intact clumps outside the Roche limit at the end of the simulations. And those can be tens of percent to even half of the moon's mass or more in some cases. The specific outcomes vary stochastically, which you might expect across different simulations. And the disk mass and angular momentum that you produce in these simulations is consistent with, as the disk evolving, ending up with a lunar mass moon outside the Roche limit and the rest of the disk accreted by the Earth. Okay, so if this were, as I like to put it, if this were a typical problem in planetary science or astrophysics, in which
we only know about constraints that we can infer from properties derived from remote sensing, okay, like the masses and the angular momentum and the bulk density. We would likely have declared victory and moved on. And yet this is a very different type of problem because we actually have samples of the moon, both from the Apollo samples and from lunar meteorites, which we can identify as such given the properties of the Apollo samples. This brings a number of constraints to this problem that have proved very challenging for the giant impact to explain, and really have motivated what in the last 10 to 15 years have been more papers on this topic, I think it's fair to say, per year than ever before. So the most challenging constraints relate to the isotopic composition of lunar rocks compared to rocks from the Earth's mantle. The issue is that across many elements, indeed across all non-volatile elements, the Earth and the Moon appear to have essentially identical composition. This plot shows the case for oxygen. So this is just one of the elements where you can see this similarity between the Earth and the Moon. So on the y-axis, that's the abundance of O17 compared to O16. On the x-axis, you have O18 compared to O16, and that's ratioed to some reference standard and typically shown in units of per mil, as here. If you take different samples from the Earth, one from the ocean, another from a cloud, they will fall at different positions on this plot because geological processes like condensation and evaporation and even differentiation in silicates will fractionate isotopes, but they fractionate isotopes in a manner that depends on the mass of the isotope. And so what that means is that all samples that you get from the Earth will fall on a single line on this plot. And the line has a slope of about 1/2, and that's just because the difference in mass between O17 and O16 is half the difference between O18 and O16, shown on the y-axis. So that defines this terrestrial fractionation line. Now, if we look at meteorites from Mars or that we think are derived from the asteroid Vesta, they have completely different and offset lines. And these are thought to represent different compositional reservoirs in the protoplanetary disk. And we describe that vertical offset by cap delta O17. Okay, the moon samples, when plotted on this plot, fall exactly on the terrestrial fractionation line. We knew this as soon as we saw the Apollo samples, but there was still a lot of error in those early simulations. Over time, they've become more and more precise, and those moon values have fallen right on top of the terrestrial line. So the difference between Mars and the Earth is some 30 times as big as the difference between the moon and the Earth, which is really small and even hard to resolve. So here's the isotopic crisis. We saw that the canonical impact makes the disk primarily from Theia, and yet all of the other data we have on what other things in the solar system look like from meteorites and meteorites from Mars suggest that Theia would likely have been isotopically different from the Earth, as indicated schematically by the different colors here. And if so, you end up with a disk and a planet after the giant impact that have very different compositions, and you'd expect the moon to be isotopically distinct, and yet it's not. Okay, so let's go one step further to put some numbers on this. We can define a compositional deviation percentage. So here I'm calculating the fraction of the final disk that originated from the target's mantle, ratio to the fraction of the post-impact planet that was derived from the target's mantle. And if we imagine a Mars-like Theia, and actually I've even allowed the impactor to be somewhat more Earth-like than Mars by about a factor of 3, but okay. Then you would need the absolute value of this compositional deviation percentage to be 10% or less to be consistent with how close the Earth and Moon are today. So the plots on the right, the upper row shows a bunch of impacts with that same impactor size that we saw in the simulations. On the left is the final system angular momentum and the predicted mass of the moon based on the properties of the disk. And if you want to match the mass of the moon and the angular momentum, you want to be inside the green box. And those are the canonical impacts that match that really well. Those same impacts, if you look at the plot on the top right, have huge compositional deviation percentages, -80, -90%, nowhere close to being in that upper green box that would be consistent with having an isotopically different Theia hit the Earth and then end up with an Earth and Moon that had the same essentially composition. So an obvious first thing to try was to try somewhat more head-on impacts, a little bit higher impact velocity, a little bit larger impactor, because those tend to make disks that are proportionally more target dominated. And those are the plots on the bottom. The bottom right plot shows you do make more target-like disks, but you're still not nearly close enough to be within that green box. The compositional difference is still way too big. And in addition, and this is the bottom plot on the left, you're now no longer consistent with the Earth-Moon angular momentum either. So this is what Jay Milosh originally called the isotopic crisis for the impact theory. And it's prompted a thorough re-examination, I would say, of every one of the assumptions that is part of the giant impact model. So I'm going to talk through 3 possible solutions to this crisis. There are more that have been proposed than just these 3, but these are the 3 that I think are the leading contenders in my mind. Possible solution number 1. What if Theia just happened to be isotopically Earth-like, much more so than Mars or meteorites from parent bodies in the asteroid belt? So to assess how likely it was, for example, that the giant impactor, that Theia itself accreted from a region close enough to the Earth and the disk that it might have had a similar isotopic composition, multiple works have imposed an initial gradient in oxygen composition in the disk, coupled that gradient to n-body simulations of terrestrial planet accretion, and then looked at the statistics of where objects in these simulations form and where they end up to look at the fraction of cases where the final large impactor on an Earth analog that is growing in one of these simulations originated, and what fraction of time did it form close enough that it would have a similar composition. And different works have gotten different answers. The most pessimistic say maybe 1% of the time you'd get this compositional match by virtue of having formed nearby. But the most optimistic cases, and I have the most optimistic estimate shown here in this plot, perhaps that likelihood might be 20%. Well, that doesn't seem too bad for a problem in astrophysics, 20% likelihood, you know. So early on, this seemed very promising. And it was really an isotopic similarity developed or appreciated in 2015 that has changed the nature of this debate and made this type of solution much more difficult. And this relates to the isotopic composition of the Earth and Moon in tungsten. So there's a very interesting system of hafnium tungsten that's used to date core formation. In the early solar system, there was a particular isotope of hafnium, 182 hafnium, that decayed to 182 tungsten with a half-life of about 9 million years. Hafnium is lithophile. That means it tends to stay in the mantle of a planet. And tungsten is a moderate siderophile. And that means as a metallic core in a planet forms, most of the tungsten present at the time will be incorporated into the core. Okay. So as a planet has its core form, or you can think of it as completes its core formation, most of the tungsten that's present in its mantle when the core forms gets pulled into the core and removed from the mantle. But if this core formation has occurred while there is still live 182 hafnium, in other words, if it's formed within, say, the first 60 million years of the solar system, then after the core forms, there will still be some 182 hafnium in the mantle, and it will generate radiogenic 182 tungsten in the mantle. And there'll then be an excess of that isotope that was produced radiogenically compared to the other isotopes of tungsten, which were preferentially pulled out into the core when it formed, okay? The earlier the core forms, the bigger this mu 182 tungsten excess in the mantle will be. So in this way, the tungsten isotopic composition of a sample does not relate to the compositional reservoir in the protoplanetary disk. It doesn't match where you formed, the feedstock from which you formed. Instead, it reflects the timing and even the chemical conditions of when your moon formed. I mean, when your core formed, rather. So if we think about the protoearth, which being more massive may have had its core form much later than that in Theia. Maybe Theia's core formed in just a couple million years. That's about when we think Mars's core formed, and Theia's the size of Mars. Then you would expect that before the collision even, Theia and the protoearth would have completely different tungsten isotopic compositions in their mantles, even if they form from the same reservoir in terms of oxygen. So this now presents quite a problem, because now you have a separate, independent coincidence required to produce an Earth and Moon with like tungsten compositions. And the plot on the right shows the likelihood of that, again, based on in-body planet accretion simulations. And it's only a few % of the time that just by chance, you end up with a relatively late formed Theia and a relatively early formed protoearth that have the right mixture, so that in the end, you get the inferred equality in tungsten isotopes. So a very small probability times that other small probability starts to become a very worrisome set of coincidences to require. So I'm going to show you some work that's in progress right now where we're scrutinizing the interpretation of the tungsten isotopic constraint. So the plot on the left is the real data. Okay, so you can see here, so here are all the lunar points from the lunar samples. And here is, by convention, the terrestrial values set to 0. So you can see currently there's an offset of about 25 ppm. That initially the Earth and the Moon were equal. In other words, that the Earth values, instead of being here, were here, is based on a model of what accreted to the Earth after the Moon forming impact. So from the abundances of highly siderophile elements in the mantle of the Earth today, it's inferred that there was a late accretion of material of half to a couple % of an Earth's mass after the Moon formed. And if you assume that this material was delivered by small, undifferentiated material that had bulk chondritic or bulk solar system composition, then as that material was added to the Earth, it would have caused Earth's mu1A2 tungsten value to become more negative, so that the observed 20 to 30 would correspond to an initial condition where the Earth and the Moon were equal. In other words, that the bulk silicate Earth was originally here. The late accretion of the small undifferentiated chondritic composition material brought it over here and generated the difference that we see today. However, there are now several arguments that suggest that this late accretion would not have been really small undifferentiated things, but would have included and perhaps been dominated in mass by large objects that themselves were differentiated into mantles and cores. You can imagine if you just had an impact by a Mars-sized object from the Moon, it's pretty probable that there'd still be a few lunar-size or 1,000-kilometer class objects still around as well. And when you look at what happens to the impactor metallic core versus mantle in these types of impacts, the core from the impactors that are large and differentiated preferentially gets accreted onto the Earth's core. And so the net contribution of material to the mantle is not chondritic anymore. And in fact, it tends to be in the opposite direction, tends to be positive. So if you have a late accretion dominated by larger objects that are differentiated, the interpretation changes. Then the initial bulk silicate Earth is actually over here, brought to its current location, so that initially the Earth-Moon difference could be as large as 100 ppm. That makes about an order of magnitude difference in the likelihood of getting this match. So this is promising, but it's still in process, and the biggest challenge here is to link this type of late accretion model to the specific depletion patterns seen in the highly siderophile elements in Earth's mantle. So that's what we're doing right now. Okay, let me see how I'm doing on time. Okay, possible solution number 2. What if we initially had a disk and a planet that were isotopically different, but then the vapor components of the disk and the planet mixed before the moon accreted and equilibrated their isotopic compositions? This was an idea first proposed by Pahlavan and Stevenson. So to explore this, we need to think about how we think this pre-lunar disk would evolve after the giant impact. So this is what I would say is a more traditional set of models for how that might happen. After canonical impact, as I mentioned, you have a melt vapor disk. About half of the disk is inside the Roche limit, which is at about 3 Earth radii for silicate densities. About half the disk is outside. The traditional view has been that the vapor component of the disk would have a low intrinsic viscosity, that it would not be subject to MRI, for example. And we'll talk about how this could differ substantially if MRI was present in the disk. But the traditional assumption has been that the vapor was relatively inviscid. But in that case, we know that in the melt component of the disk interior to the Roche limit, there would have been a viscosity. So from planetary ring studies, from n-body simulations, from theoretical arguments, we know that interior to the Roche limit, if you have a disk of condensates, they will tend to clump due to local gravity, and these clumps will get sheared apart by the planet tides, and then they'll form these trailing spiral structures seen in this n-body simulation here, and that these produce a spreading of the disk and a viscosity interior to the Roche limit. And the form of the viscosity is shown there. It's proportional to the melt surface density squared. Now, exterior to the Roche limit, this doesn't apply because if you have clumping or collisions, things can remain bound outside the Roche limit. So it's in that region where you would have the moon actually start to accrete. At least that would be the closest it could accrete. So the picture developed particularly in papers by Bill Ward was a coupled thermal and phase balance in the disk, in which you have heat generated from viscous dissipation in the melt layer and from any condensation that's occurring, because latent heat, it's a big energy budget in this problem. And that's balanced by radiative cooling from the surface of this disk photosphere. And the melt layer adjusts its surface density so as to maintain this balance. And that corresponds to a total mass in that melt layer inside the Roche limit of about 15% of a lunar mass. Then as the melt spreads both onto the Earth and outside the Roche limit, additional condensation from the vapor layer can occur. And then overall, the system evolves on about a 100-year time scale, the time to radiatively cool away that latent heat from the vapor phase. So back now about a decade ago, we developed a simple model to try to capture the main elements of this description. We couple an analytic model for the disk inside the Roche limit to an n-body accretion simulation outside the Roche limit. Things that grow in the outer disk interact through the strongest resonant torques with the inner disk. And as the disk viscously spreads, new moonlets are spawned and added to the outer part of the disk in the simulation. This naturally leads to a 3-stage lunar accretion that we'll see in this simulation. There's an initial phase, extraordinarily rapid accumulation of whatever melt is in the outer disk initially, even if you don't place a big clump there initially. Once a large moonlet forms, it shepherds the inner disk inside the Roche limit, and there's a stall in the lunar growth for a period. And then there's a final phase of lunar growth as material from the inner disk spreads onto and is accreted by the moon. So we already missed the initial phase where we accrete a moon. You can see that it's the disk is being shepherded within the Roche limit. It spreads back out and starts to spawn moons there. The yellow circle around the moon is the portion of the moon that came from that inner disk. The inner disk mass is decreasing with time as it's viscously spreading. And eventually you move into a scattering regime where material is more likely to be scattered back into the disk and ultimately accreted by the Earth than it is to end up on the moon. What these types of models suggest is that this initial portion of the moon that forms from the material from Theia that starts in the outer disk, it's really hard to imagine how this gets equilibrated with the Earth's composition. It's already melt and it clumps so quickly. In contrast, this material from the inner disk that may persist as long as 100 years or may be very actively mixed, this could be equilibrated perhaps. And so from this came this idea that perhaps the moon's composition is heterogeneous with depth, with the first accreted inner parts of the moon, more Theia dominated, and the outer portions of the moon, which are mostly represented by the samples that we have, being more equilibrated and Earth-like in their composition. And indeed, there are some hints that as you look, for example, at Cap Delta 017, that the samples that we think are sampling greater depth are more different from the Earth. The challenge here is we really have very few samples that are sampling the moon at depth. Almost all the samples are from the upper crust. And so there's very little data here. Okay, so those traditional models have presumed that the vapor component of the disk was inviscid or had a very low viscosity. What if that's not true? In particular, could we have had an ambient magnetic field? Because we know that if we did, then MRI could power a very high viscosity and rapid spreading and perhaps mixing of the disk. So we think that a global planetary field is generated as a result of convective motions in a liquid layer of its core that sustains a dynamo. It's generally thought that there are both thermal and compositional gradients in the structure of the core that develop during particularly these late stages of planet accretion that may tend to oppose that convection. For example, each time you have a giant impact, the metallic core from the impactor often merges right on top of the core of the target, and it's more highly heated and tends to create a positive radial temperature gradient in the core that's the opposite to what you'd want to have sustained convection. And yet, it's been suggested that if you have a really big impact, and this is Rees and Solomatov, you might be able to sustain a dynamo just within the layer deposit on top of the target core by the impact itself. So it's certainly plausible that we could have had a field. And this is something that's been looked at by Patrick Mullen and Charles Gammy and Carbolito et al. Most importantly, in the recent Mullen and Gammy paper, they showed that if you had a seed field present, then you can amplify that field due to either magnetic winding in the disk or from full-on MRI turbulence or both. And these are two different simulations from that paper showing an extremely small background field and then a very large background field. So to date, there really haven't been models for how the moon would form after in this type of condition. But there have been some general arguments made. MRI could drive mixing between the proto-earth and the disk vapor. The inner disk, the thermal balance I described before doesn't apply. If you had MRI, the inner disk would fully vaporize and it would rapidly spread. So that second phase of lunar accretion, it would all happen much faster, we think. Because MRI transports angular momentum, you'd lose a lot more mass to accretion on the Earth. So the moon's overall incorporation of that inner disk material might be reduced in efficiency. But at least for the canonical impacts, because the material placed outside the Roche limit initially is 80 or 90% melt, it already has large clumps in it, it accretes into a sublunar size object in a matter of days to weeks. That material probably still would not be equilibrated, I would guess, although this is an area that merits more work. Okay, so we talked about an isotopically Earth-like Theia. We talked about the potential for disk-planet equilibration. Now we're going to talk about a third idea. can you identify an impact that would just produce a disk and a planet with the same isotopic composition directly? So not the canonical impact, right, but something else entirely. And the answer is there are an extremely small number of impacts that could do this. And the case I'm showing here is what I think is the best candidate. In this type of collision, Theia and the protoearth are similar in size. That's why it's called the half-Earth impact. The impact's very low velocity. It produces a very rapidly rotating intermediate structure. The metallic cores, that are higher density, of course, of both colliding objects rapidly migrate to the center. And you have what, if you're familiar with these old attempts to form binary stars from fission simulations, looks a lot like those simulations. You have a bar type mode that forms here and a trailing spiral structure out each end. These trailing spiral structures are very effective at angular momentum transport across them. And the result is a quite massive disk containing about 3 to 5 lunar masses. Why this produces a disk and a planet with the same composition, very simple to understand. You can imagine in the limit of 2 identical objects colliding, if they formed a planet and a disk, then just by simple symmetry, at the end, the disk would be half from object number 1 and half from object number 2, and the planet would be half from object number 1 and half from object number 2. Now, you would never have a completely symmetric collision, but what we've shown is even if it's somewhat asymmetric, specifically if Theia has a mass of about 40% of the Earth's mass or more, then you can get close enough to where the compositions after the impact are extremely close to each other, and they can have a delta FT even of 0 sometimes, okay? So this gives you a massive disk and the like compositions, but it also leaves a system with 2 to 3 times the angular momentum in the Earth moon today. Big difference. So I'm going to spend the last portion of the talk describing a mechanism that may be capable of removing that angular momentum excess to make a high angular momentum impact like this consistent with the Earth moon we have today. And this is an Earth moon sun resonance known as evection. So the moon's orbit precesses, of course. This is apsidal precession, primarily due to the Earth's oblateness. It's J2 due to its spin. As the moon's orbit expanded after it formed, the precession period lengthens, and evection occurs when that period is 1 year. So when it's commensurate with the Earth's orbital period around the sun. And when trapped in evection, the longitude of the lunar periapse and the longitude of the sun, the difference between those 2 angles librates between plus or minus pi over 2. So it's either oriented like this or oriented with its periapse on that side like this. And this orientation is maintained then as the Earth goes around the sun, and it librates around those stability points. If you just put the moon in this resonance, its eccentricity and this resonant angle phi will oscillate, but there'll be no net torque on the Earth-Moon system. However, if you add in tidal evolution of the moon's orbit, there is a net torque, and angular momentum is transferred from the Earth-Moon pair to the Earth's orbit around the sun. This was seen in simulations in the late 1990s by Tuma and Wisdom, who looked at capture into evection after a canonical impact and found that it was very short-lived, and it only changed the Earth-Moon angular momentum by about 10%. And that had already been accounted for in models of the canonical impact. But then in 2012, Shook and Stewart considered capture into evection around an Earth that was much more rapidly rotating, as would be the result of one of these high angular momentum impacts. And they found a very different answer: long capture into resonance, and that for a particular range of tidal parameters in the Earth and the moon. And these are, the ratio of these parameters are typically expressed by capital A. So we've got the love numbers and the tidal quality factors and the moon and the Earth, as well as their masses and radii, that for a certain range of that capital A, no matter where you started in angular momentum, evection would always bring you back to the Earth-Moon angular momentum. So that seemed very compelling. So here's a set of their results The moon initially expands on a low eccentricity orbit until at this point, at about 7 Earth radii, it's captured into evection. Once it's captured into evection, then as the semi-major axis is increased due to tides, the resonance increases the eccentricity of the lunar orbit so as to maintain the precession rate of 2 pi over a year, to maintain that resonance condition. When the eccentricity of the lunar orbit, there we go, gets very high, tides raised in the moon start to become important and actually overwhelm the effect of the tides on the Earth that cause the moon's orbit to expand. And the moon then enters a prolonged period where its orbit is contracting at high eccentricity. And it's during this period of time that the Earth's spin is then slowed from just under 3 to 6 hours. Incredible angular momentum transfer. And during this time, Shook and Stewart found that the object stayed in formal evection resonance the whole time. So immediately after this paper came out, very high impact paper, one of the initial concerns raised was that the tidal model used in these simulations was not a standard one. It was very simplified. And we know that the angular momentum drain associated with evection depends on the tidal model. So Wisdom and Tian, this was the first their paper. They also had Tian et al. In 2017. They implemented a full constant lag angle tidal model, the Darwin-Kalla model. And when they redid the simulations, now you can't actually see this. The line is not showing here. So you want to have this, the system end up at 1 on this y-axis. And these triangles are the Shook and Stewart results that I mentioned. You know, no matter where you start in this region, you always end up at the Earth-Moon angular momentum. Wisdom and Tian found that region of parameter space actually removed too much angular momentum. Then in another region, Wisdom and Tian saw something odd in which the angular momentum was removed from the system, even in cases where it was clear that the resonant angle was not librating. So it wasn't in formal resonance. And they called this a limit cycle. So we developed a complementary analytic model. The goal here was to try to survey parameter space and tidal parameters, which are very uncertain. Okay, so you'd like to understand how outcomes vary with tides and to understand this nature of what Wisdom and Tian had seen in their simulation. So this is a relatively simple system, planar approximation. So you're assuming the obliquity of the Earth and the inclination of the moon's orbit were both small. We compute the change in the lunar eccentricity and the resonance angle due to the sun and due to the quadrupole of Earth's field and use Lagrange's equations to get those rates. We implemented the Mignard tidal model. For those of you familiar with these, this is a constant time delay tidal model in which the lag angle of a tide reflects that time and then the differences in position of the objects. This leads to 6 couple equations that one can integrate much more quickly than the direct orbital integrations done previously. So let me show you some of the results, which I think have been quite pedagogically helpful. So the plot on the left is, so we've got an Earth-centered frame. We're looking down on the Earth moon. So the moon orbit in orange, the evection resonance position will be the dashed circle. Top right plot will show the total system angular momentum, the angular momentum and the Earth spin over time. And the bottom plot shows the precession period of the moon versus time. So when it's captured in evection, this is 1. And then this increase in the libration angle here is associated with resonant escape. And then we'll talk about this interesting phase. So initially, the moon's orbit is inside evection. It tidally evolves outward. And you can see that during that interaction, the angular momentum of the Earth-Moon system is constant. The Earth encounters evection, and it's captured in it. Oops. Sorry, let's see if I get to do the next one. Sorry, I've hit the wrong place on my slide, and so we'll have to suffer through the first phase of this evolution again. So once it's captured in evection, you can see its eccentricity growing. It's maintaining this alignment. It's in resonance proper. And during that phase, some angular momentum is lost. At this point, the moon is nearing the point at which its orbit begins to contract. And near that point, the libration amplitude increases and the moon escapes the resonance. And this angle starts circulating, which is, you can see that shape on the plot. The phase here labeled as 3 in the bottom plot is what we've called a quasi-resonance. What's happened here is when the moon escapes evection initially, it's just inside the position of evection. And the moon's orbit's contracting during this phase. It's getting closer to the Earth. Evection is outside of it, but evection is contracting as well because the spin of the Earth is being slowed and the J2 of the Earth is slowing. And evection, the position of evection, is actually converging from the outside on the moon's orbit. And so evection maintains the moon's eccentricity at a high value, even though the moon isn't formally librating in resonance. And this continues until finally evection crosses over the moon, and then the moon gets outside evection, and then this quasi-resonance period ends, and the Earth-Moon system go about a standard two-body evolution. And so for this case, we've picked particular values that take us from a high angular momentum impact all the way down to an Earth-Moon system, angular momentum. But what we find is there's nothing special about a final state at the Earth-Moon angular momentum. So that's very different than the Chook and Stewart original result. So these are results of many simulations. The color is the final system angular momentum. So you have that capital A, the ratio of the tidal parameters in the moon to the Earth. And then on the x-axis, the absolute rate of tidal evolution. And what we see is many cases where Earth tides are initially slow remove way too much angular momentum. They go all the way to the dual synchronous state, the Pluto-Charon dynamical state. Whereas with fast tidal evolution, very little angular momentum is removed, and this quasi-resonance phase really barely occurs. And if you're very judicious, I think that's a good word for this, if you pick your values correctly, then there's a shaded, which is appearing very light on the screen, area where you can get the Earth-Moon angular momentum, but it's one option out of many. So right now we're investigating by incorporating physical models for how these tidal parameters would change with time in the early system. We think that initially both Q of the Earth and capital A would be large. So we'd be over here. And then as the moon's mantle started to solidify, that Q of the Earth would decrease and we'd move like this across this plot. So possible to remove the needed angular momentum. Not clear that it's probable yet, but still promising. And I should also mention that there's at least one other mechanism that's been proposed to remove this level of angular momentum. I would say it's no simpler than this. Okay, so let me finish up. We now know that most of these big low velocity impacts that you need to accrete an Earth-sized planet to begin with, we think, will also have made disks. So we expect that planets probably had transient moons as they were forming. However, the specific properties of the Earth-Moon have proven to be extremely challenging to explain. We talked about 3 possibilities, an isotopically Earth-like Theia. Tungsten is the real fly in the ointment there. A canonical impact followed by equilibration. For a canonical impact, it seems that this would lead to a heterogeneous composition for the moon. Not clear yet whether that matches with the moon we see. And then a high angular momentum impact that gives you a match between the composition of the disk and the Earth, but needs this angular momentum removal. Multiple other proposed ideas exist as well, including scenarios that are a mixture of these that may require both some disk planet equilibration and some angular momentum removal, or maybe even forming the moon by multiple impacts. So what do we need to do to make progress? Hopefully to start removing some of the possibilities and zeroing in on the most promising ones. Many thousands of impact simulations have been done. I've mentioned that. By comparison, very little energy has been spent on models for how the disk evolves and how the moon actually forms. And yet those are the models, we hope, that ultimately will link these energetically quite different models to observable properties of the moon, whether it's the moon's isotopic composition, its composition at depth, its initial thermal state, things like that. The nature of the late material accreted onto the Earth after the moon forming impact relates both to the isotopic discussion that I mentioned, but also to properties of the early lunar orbit. That's important too. And there are specific pieces of lunar data that would really help progress. The composition of the moon at depth, again, most of our samples are from the upward crust. Whether the moon was fully or only partially molten, how deep was the initial lunar magma ocean? It turns out it's extremely challenging to avoid melting the moon entirely after a giant impact. And a lot of the current data on the moon suggests the moon was only partially molten. And if that's true, then that is really going to constrain our theoretical models. And the early bombardment record on the moon, both for constraining late accretion and the dynamics in the outer solar system, in the early system as well. And this is my final slide, which is to say that we are hopeful that we're going to get some fantastic data from the moon in the next decade. We just completed, as Patrick mentioned, we just completed our decadal survey in planetary science and astrobiology. I was honored to co-chair that. One of the big prioritized missions that came out of that survey is described here. We call it Endurance A. This is a long-range robotic lunar rover that would traverse the far side of the moon. This is a much more ancient in general part of the moon than the near side explored by Apollo. In particular, within the largest and oldest impact basin on the moon, which is this SPA basin shown here, it would collect 100 kilograms or more of samples and bring them back to the planned Artemis base camp at the South Pole for return by the Artemis astronauts. 100 kilograms, to put that into context, this is an Apollo-like sample set. When we have thought about robotic missions to the moon before to bring back samples, you know, these are grams of sample return. This would be an Apollo class sample set, but from the backside of the moon that could really allow you to do multiple things all at once. It's essentially a sample return campaign in a single mission. You can date the oldest basin. You can date a basin superimposed on that. So you get at least 2 data points on the early bombardment rate right after the moon formed. Access areas of SPA that should have exposed mantle material from the moon because of the size of this impact, and answer questions like, is the moon's composition heterogeneous at depth? So with that, I will stop and take questions. Thank you.
I have a question about the impact of this evection resonance on the moon itself. So you mentioned that the dissipation of the orbital energy, the shrinking of the semi-major axis of the system, happens due to the tides in the moon. This is a substantial amount of orbital energy that needs to be dissipated, and judging by your plots, in a relatively short amount of time. So do you or somebody else have thought about what that would do to the moon? Would this melt the central part and create magnetism? Or maybe it will melt the whole thing and reset this, like the cratering record on the moon.
Yes, you have anticipated the work of Tien et al. 2017. So this is Jack Wisdom and Lindy Elkins-Tanton and Tien. So this plot here, we are holding the tidal properties of both the Earth and moon constant, but they would not be. There would be a feedback that would exist. For example, if you actually drove the moon to high eccentricities, like the example I showed you, then that would drive heating in the moon, and it's a lot of orbital energy, as you are correct. And Tien et al. Showed that the original high eccentricity evolution identified in Shook and Stewart, once you account for melting of the moon due to that deposition of energy, the tidal properties of the moon then change and it pops out of resonance. So it'll still be melted. And so essentially the plot on the left, Tien et al. Later argued that not only did this evolution leave systems with too little angular momentum, it would never occur to start with because of the feedback you just mentioned. Now, these evolutions with high A, the dynamics looks the same, but the eccentricities always stay much lower. And so that's actually the preferred mode, is to have A not of 10, which makes the eccentricity large, and it most obviously seen in the animations, but to imagine an evolution in which the eccentricity of the moon only got to say 0.05 or 0.1, then you can keep a coherent picture for the angular momentum removal, even when you account for the effect you just described. So yeah, great question.
You argued that satellite formation is common in the late stages when there's a giant impact. So why don't Mercury, Venus, and Mars have any significant satellites?
Yeah. So with Mars, believe it or not, even though the two tiny moons, Phobos and Deimos, were often attributed to capture because spectrally they look like asteroids, the leading model, I would say, for the origin of that system is that Mars had a giant impact by something smaller in scale than this, but by a Vesta-like object, and that it initially did have a larger inner moon that tidally evolved inward and was eventually lost. With Mercury, with a slow rotation, a moon, if you have one, will tidally evolve inward and be lost. Venus is a really good question, and I don't think we have a compelling answer for that. So there are models for getting to Venus's retrograde, slow rotating state right now that start Venus at a higher rotation rate. It's not 2 hours. Typically, those models consider an initial Venus with a rotational day of, say, 10 hours or so. From the terrestrial accretion simulation, you would think that Venus should have had several moon-forming giant impacts as it formed. And so did you have evection, or did you have two impacts, a first that made a moon and a second that was in the opposite sense, so it tidally destabilized that moon? Those are the kind of ideas out there, but there's not a really compelling well-constrained explanation for that, I would say.
Late accretion could drive the isotopic anomaly in either direction, depending on whether the bodies, the impactors, were large enough to differentiate themselves. I would have thought that the crater size distribution on the moon would shed some light on the size of the impactors. You know, is Tycho, for example, large enough to have been formed by a differentiated body?
So generally, and I'm inserting the word generally because the size at which objects would be expected to be differentiated depends on when they accreted, because a major source of heat, if they accreted early, was the decay of aluminum-26. But if you imagine objects forming within the first few million years of solar system history, then by the time you get to objects that are hundreds of kilometers across, you would expect them to be differentiated. So the types of impacts that we're envisioning, so if the moon forming impactor, if Theia was of order 0.1 Earth masses, these would be 10 to the -3 to 10 to the -2 Earth masses. These are 1,000-kilometer objects. These would have been differentiated. In terms of the size distribution of objects, you can back out size frequency distributions from the crater record. And those are the classic, even if you have a distribution where most of the mass is in the largest objects, by number, the smaller objects are more plentiful. But it's those types of distributions that I mentioned that make it seem really unlikely that you would have a Mars-sized Theia hit the Earth and then never have anything after that hit it, except things that were sub-100-kilometer in size. If you look at those standard size distributions that we get from the crater record, they imply these roughly power law distributions in the number versus size distribution of background stuff that says, yeah, there should have been some lunar size or somewhat smaller things still around. So that thinking is kind of built into that concept.
One last question.
Yeah, I was wondering about the difference between the Earth-Earth or proto-Earth collision compared to just having the giant impactor, because in the former case, I guess you would get very strong differential rotation in the core of the merged two Earths. I was wondering if that either leaves some imprint in the composition or in the generation of the magnetic field that you would expect.
Okay, I'm going to have to, I missed the very first part of your question. Could you just repeat the very first part?
Right, I'm basically asking, if you merge two equally sized objects,
Yes.
you probably end up with a very strong differential rotation profile inside the core.
Yes.
And I wonder if this is different from having like a star, the Earth just being hit by some smaller impactor. Has any imprint in terms of composition in the core or in terms of generation of magnetic field yet in the Earth?
So you're absolutely right. Your the specific angular momentum in the merged product after the half-Earth impact much higher than the traditional canonical impact, and in particular that core is very rapidly rotating. There's been some discussion by Nakajima and Stevenson about, this is not related to fields, because I really think to a large degree how magnetic fields affect this problem has really only been considered by a couple works. But in terms of the internal mixing, Nakajima and Stevenson looked at how the strong differential rotation in these high momentum impacts would be expected to produce extensive mixing in the Earth's mantle, just through shear instabilities. Why is that important? Another isotopic discovery that is really fascinating, and it also involves tungsten and several other species as well. In the Earth, they have identified particular rocks in the Earth that show isotopic anomalies that they think predate the moon forming impact. They're that old. So the default interpretation of the existence of those anomalies is that, amazingly, the Earth's mantle cannot have been completely well mixed by the moon forming impact. And that's actually one of the arguments against these high angular momentum impacts, because we think we see evidence of unmixed primordial stuff from probably the core mantle boundary of the Earth. So great question. Thank you.
Thank you.